Hello again. Yeah, I've just brought a bunch of these GU10 LED fittings for a large installation I've got coming up shortly. Yeah, these are the 4 watt versions. So I thought I'd take one apart and take a look at it and show you guys how they work. Yeah, here's one here I've actually taken apart. It's your usual generic capacitive dropper, and the interesting thing about these are that these are multi-chip LEDs. Actually house 3 LEDs in one chip, so I've actually measured the voltage across them. We're getting 141 volts, which equate to about 47 white LEDs, which works out as 3 LEDs a chip. Yeah, they seem well made. So what I thought I'd do is actually, I've drawn the schematic out there, I've actually reverse engineered it. I thought what I'd do is run through with you component by component and tell you exactly what they're used for. I've actually designed quite a few of these in my time, and I think what we'll do, we'll run through a few calculations and make a bit more sense out of it. So let's take a closer look at the schematic and we'll run through the components. Yeah, so there's a schematic. So we'll work from left to right. So we got R1 here. Sometimes these can be misconcepted by some folks. The purpose of that, it's got 2 purposes actually. It can be used as like a fuse, and also it's to limit the current for downstream circuit breakers, because depending on when you actually switch your light on, where the phase is at a particular time, C1 can actually draw a massive amount of current, and it can actually trip out down circuit MCBs. So we'll do the calculation on that one later and you'll see why. There we have C1 is obviously the capacitive dropper. It's an X-type capacitor. It has to be rated to take the peak voltage around 400 volts. You can't use any normal capacitor in there as it basically explode. Then R2 here, that's a bleeder resistor, that is basically, so when we switch it off, we to take the lamp out of this socket, we ain't going to get any tingles or shocks, so it just bleeds the current away. And there's the bridge rectifier. We should all know what that does. Rectifies it down to DC, AC into DC. And we've got our smoothing capacitor, just to smooth out that 100 kilohertz of lumps that you'll get once it's been rectified. R3, basically that's basically what that would be used for is when we switch the lights off, they go off very quickly rather than being held there with that capacitor. Sometimes you might see it, you switch off cheap lights and then you see them glowing in the background. It's probably because either that's been emitted or it's not quite big enough. And R4 is another misconception as well. If you've got a well-designed capacitive dropper, you shouldn't need to limit any current through there. Especially in lamps, if it's well designed, you shouldn't need any current limiting. Basically, all that is just to protect the LEDs from any surge currents coming through, and also it's a convenient place to measure the current. If you do Ohm's law, you just measure the voltage across it and work out what the current is. And then there we go. There's the LEDs. And in our in my particular fitting that I'm looking at, this actually got a 141 volt drop across it, and you get white LEDs, basically 3 volts a piece drop across them, equates to about 47 white LEDs. So I think now what we'll do now, we'll run through, there's an equation that I've always used, and there's a it's not for the beginner really, especially this part of the circuit here, because you've got R1 and C1 in series with each other. You've got to remember they're orthogonal to each other, so you have to use a bit of Pythagoras to actually get a calculation that equates to what is the current that it's delivering. But we'll look at that in a moment anyway, and we'll run through a few. And you can, the equations that I use here, the ones that I use when I design my own circuit. So we'll take a look at them. We'll take some measurements, and there you go. So they are the equations that I use whenever I'm designing a capacitive dropper power supply for LED lights. And also these are the equations I use if I ever need to solve any of these circuits that I'm looking at. So I think what we'll do, we'll solve this circuit and then we'll take some actual practical measurements to see how far out we are. We usually should be bang on the money. So the first thing we need to do is to find the capacitive reactance of C1. Capacitive reactance is effectively DC resistance, because we've got an AC current going in there. We need to find the reactance, which from now on we call reactance resistance, and that'll be equation 1. So we know that C1 is 0.75 UF microfarad. So first step is, so 10 to the power of 6, 2 times pi, 2 shift pi, times the frequency, which is 50 Hz in the UK, times 0.75 UF, 0.75, just put 0.75, we got the power at the top. So there you go, so that's 4,244 ohms then. So we make a note of that. Sorry, so that's 4,244. Let's put 0.13 then. No, 0.14 round. No, 0.13. So that's the reactance. So we found the reactance. So now we move on to equation 2. So once we've plugged equation 2 into the calculator, that should tell us what that circuit current draw is on that circuit. So let's have a look at equation 2. Right, I'll just run through it quick. I'm not going to bore you with the details. So 0.63 is a rule of thumb average that we sort of take. It sort of works out well when you times the answer to this by 0.63. VPK means voltage peak, which would be the peak voltage of 240, which to find the peak voltage we times it by 1.4. I think it's 1.41. That's right. So that equates to, say, 340 volts. Take away the V LED voltage, which we know is 141 volts. And because R1 and C1 are orthogonal to each other, you have to put a bit of oh, I see a mistake in my equation. Let's square that as well. Yeah, we effectively, because the C1 is actually out of phase, this point here and this point here, they'll be out of phase with each other by 90 degrees, so you have to do a bit of Pythagoras at the bottom. So right, I'm not going to bore you with any more details. We'll plug it in what we know, and we'll see. So 0.63 times, don't forget the parentheses, are quite important in this equation. Oh yes, that's 0.63 times voltage peak 340, take 141, I don't know if you can see that, sorry, 141. Then we take square root of squares, so we know that R1 is 20 ohms, 20 ohms squared. plus the capacitive reactance squared, which we know is 4244.13. So 4244.13 squared. I made an error somewhere there, so have a look. Sorry about this. Do that again. 0.63 times voltage peak, which is 340. Take 141. I think I've forgot the parenthesis. I think the square root of 20 squared plus 4244.13 squared equals, yeah, so that according to that we're getting around 30 milliamps. That is 4, 2, 4. No, I didn't even see that. Yeah, so we've rounded off to about 30 milliamps. So now that we got 30 milliamps, we can work out what the voltage is going to be across R4. So that's just basic Ohm's law. So we need V over R. So we need I times R, so 0.030 times, which is 44 ohms. You should be getting about 1.32 volts across that. Two volts, and finally we find out what current it's going to be drawing. So 0.030 times 141. So we should be getting around 4.23 watts. This light fit in. £3. So there you go. What else can I say? Yeah, back to this equation. Yeah, so what we'll do now is in a moment. What we do in a moment is actually take some measurements. Take some measurements of the actual fitting and see how close we are. There's also, before we do that, there's also another equation I use. Basically, I've just rearranged equation 2 around here. Just there. So you can actually design your own. So you could define C1. So basically, you know what your peak voltage is, and you're going to have an idea how many LEDs you're going to use. And also you can have an idea of what current you need circuit drawing, and that'll give you the value of the capacitive reactance. And then once you get the capacitive reactance again, you just put it into this equation number 2 down here, and that'll tell you what value you need. So that's very useful, that, especially for designing these circuits. Very important to put the parentheses in, as it won't work. what else can I say? Yes, you don't always have to use R1, the resistor at the front end, but it's good practice too, just to stop nuisance tripping of MCBs and whatnot. Oh, that's enough of that. Let's take some measurements and see how close we are. Yeah, so I've got it plugged into my very safe setup. Yeah, I think all we need to do, because we got let's go back to schematic, because we got R4 in here, all we need to do really is measure the voltage across that, and if we're anywhere close to that, we know that the circuit's going to be drawing about 300 milliamps at around 4.23 watts, and that suggests what the light is. So I'll do that now. I'll measure across R4, and hopefully we should be getting around 1.32 volts. Let's have a look. It's very fiddly here. Right, that's right, DC. That's 1.31. So we're not that far out, are we? So 1.31, 1.31 times 44. No, what am I on about? Divided by 1.31 divided into 44. Yeah, so that'd be 29.7 milliamps. So there you have it. So I know it dragged on a bit, but that suggests that our equations are right. So have a look at a few fittings yourself, have a look at that equation, and you'll find that it never let you down. There you go. I don't want to bore you with the details of the equation, run you through it, but basically all it's saying is that the higher the capacitance, the lower the resistance, hence the more current you got. So if you use that equation that I rearranged to find C, you can actually design your own circuits. Pretty reliable. It's just up to you to have a crack at it yourself. I hope that was of some use to you, listening to my boring voice waffling on. I hope I got it all across to you, and happy hunting. Thank you.